Good morning, and this hour we will talk about ship hull form and its relationship to resistance. From the understanding of resistance, it is possible for us to draw some guidelines as to how we can develop a hull form or what are the parameters of hull form that can be controlled to give better resistance characteristics at the design stage, because once the design is over, the hull form is fixed. If the resistance characteristics are not good, the ship will suffer for its entire life. So, we will see some main parameters of the hull form and how it affects resistance. This will be fairly general analysis of relationship of hull form to resistance. The parameter that affects most the resistance of the ship is the fullness of the ship, how full the ship is, represented by the form coefficients. Mainly CB and CP and C midship. We will see all of this. CB, of course, the block coefficient tells us how full the ship is and gives us some idea about how the ends are shaped, so that generally we can say that if the ends are shaped more smoothly or more narrowly, then I can get a higher speed. That means higher speed will lead to lower CB, okay, or fine form. That is the reason you will find bulk carriers and tankers are full form ships with high CB, and passenger ships, container ships, etc. are finer form. Now, you see, when I am talking of speed, I am essentially talking about Froude number, not speed as such. That is, if I have a container ship which is say 250 meters long, one of the large container ships, it can move at 24 knots. Now, what I do is I geometrically bring the ship down in size. Instead of 250 meters, now let me see, I bring it down by half to 125 meters. Every dimension reduces by half. If that was moving at 24 knots, will this ship move at 24 knots? Would it mean that it will move at 24 knots? The answer is no. It will move at a speed which will be at the corresponding speed. That means it will move at 25 divided by root 2, because the scale is 2. So, that optimum speed will be 25 divided by 1.414, which would be something like 17-18 knots of that order. So, you see, you cannot say if I have a small ship I will move at high speed, it just does not follow. The fullness remains constant. If that had a block of 0.65, this ship will also have a block of 0.65. Only the size length has come down, right, but its speed has also come down based on Froude number equality. Okay. So, we keep this in mind, speed is represented by Froude number. You may think, for example, since it is a smaller ship, I will put more power and it will go at a higher speed. Now, you can afford more power. The bigger ship had large power, you could not go on increasing the power, but you have got now a smaller ship, reduced by half, speed has fallen. So, your power is less. Say in that big ship you had a 10,000 kilowatts of power, and in this ship you have something like 3,000 kilowatts of power. Now, you may say that I add another 2,000 kilowatts, I can afford 5,000 kilowatts. If I give 5,000, I will get 24 knots. But will you? Will you? Say this is Froude number, this is CT, or we can also draw RT versus speed for that length. How will the curve be? We have seen the resistance curve goes, wave making resistance at a higher speed becomes more prominent, and it is to the power of 6, varies to the power of 6. So, somewhere after this speed, somewhere around this speed is my optimum speed. Anything more than this, the power consumption will go up tremendously without any further addition of speed, appreciable addition of speed. So, every ship will have a optimum speed, and if you reduce in scale, that optimum speed will come down based on Froude similarity. You cannot just go on adding power and say the speed will go on increasing, that does not happen. So, how does, or let me say, the next important characteristics apart from fullness of the ship is how the displacement is distributed over the length of the ship. How do you represent this? How does the volume of displacement get distributed over the length of the ship? Do you know how it is represented? You should know. Sectional area curve. You know this? Are you aware what is a sectional area curve? Are you aware? Yes or no? Okay, if you are not aware, I will have to draw it for you. This is the forward perpendicular of the ship, this is the aft perpendicular of the ship, and somewhere here is the midship. Let us say here is the midship. So, I know if I draw this, this is length dimension and this is sectional area. You know what is sectional area, no? Area of the section. If I draw this curve, then here will be the midship. Midship section is so much, A midship, which we have talked in the previous hour, and it may be 0 a little aft of AP if my transom or the stern is immersed in AP. Then AP is at the rudder stock, there may be some portion still to the after. So, at the somewhere here it will become 0, and similarly if I have a bulbous bow, let me assume there is a bulbous bow, there will be area forward of the fore perpendicular, and it will become 0 at the end of bulbous bow, because remember the ship, if this is the FP, the ship's waterline and FP will coincide at low rudder line, and if there is a bulbous bow it will go like this. So, sectional area curve below the low rudder line will end at the end of the bulb, right. So, this end comes here, and if I draw this curve, it will look something like this. If I draw the sections and join them by means of a curve, this is how I will get it. Now, this gives me the distribution of sectional area over the length of the ship. Okay. What else does it give me? The area under this curve gives me the volume of displacement, and the moment, if I take the moment of this curve about any point, then I will get where the LCB of the section is, of the ship is at low rudder line. This is the at low rudder line. Okay. What does this curve show me? it tells me that a portion of the ship's length from here to here is constant, is giving constant sectional area. Therefore, the section is constant. So, this is what we call parallel middle body, and this I call entrance, and this I call run. Okay. Let us look at this diagram. If I change the parallel middle body, how it will look? If I change the PMB, suppose I want to increase the parallel middle body. See, if I have a longer parallel middle body, it is easier for me to manufacture, because I am manufacturing the same section for a longer length, is not it? So, I may be tempted from production point of view to increase the parallel middle body. Let us say I take it up to here in the forward part. Obviously, if I take it down parallelly to this curve, I will have more volume in the than what is desired. So, I can't do that. What I will have to do is, if I take it out from here, I have to bring it down somewhere here, right. So, that this volume is equal to this volume, right. Now, which of these curves is better? This one? You mean this one is better or this one? Let me write 1 and 2. This curve is 1 and this top curve is 2.
One is better resistance point of view.
So that tells a forward part where we are getting blockage is less in forward part in the starting.
So, you mean to say 2 is better, and you are saying 1 is better.
Resistance point of view.
Okay. Now, we have a problem. We have both the forms coming out as better. It is very difficult to say which is better, but we can make some general statement. If my forward part is narrower, then it generally says that my forward part is narrower. If the sectional area curve is less at the fore end, then I can generally say my fore end is narrower. Whether it is better or not, I will know only when I do my 4 sections. We will come to that. But what does this portion show? Shoulder. In the case of curve 2, in case of this curve, curve 2, the shoulder is more prominent, and in case of curve 1, the shoulder is less prominent. Now, we have seen about wave resistance, wave making resistance. The curve 2 will give me a more prominent shoulder wave. So, looking at it from this point alone, I would prefer curve 2 to be worse than curve 1. That is, I will prefer curve 1, where I have a smoother shoulder. Understood? Therefore, generally less parallel middle body for the same volume is better from resistance point of view. Of course, you cannot have this, you have to have compromises always. How much parallel middle body? If you have one advantage of parallel middle body is, if you have some parallel middle body, you can reduce something and get a different length of ship, depending on the requirement of a owner.
Interior space increases with 2 and decreases with 1 volume.
To some extent this is true. Volume as such will remain same, interior volume will remain same, but the cargo space becomes more organized with 2, no doubt, no doubt about it. But definitely the shoulder effects matter. This also the same thing. For the same reason, the LCB plays an important part in resistance. Longitudinal center of buoyancy. It indicates how much volume is in the forward and how much volume in the aft, isn't it? So, if in my design, if the forward portion is giving me a major effect of resistance, then I should adjust my LCB accordingly. Maybe I require to move the LCB aft. So, my aft becomes full and forward becomes finer, maybe, but that is not always the case. This is the case generally for fast ships, fast fine ships, that I move my LCB aft, so that my forward portion is finer. But in full form ships, just the reverse occurs. I may have large amount of separation coming up in the aft. So, I may like to refine my aft more than my forward, where wave making is not a major component. I may like to shift my LCB forward. So, as the block coefficient goes up, the LCB starts moving from aft to forward. This is general. I am only talking to you how the parameters get affected due to resistance. I am not saying these are guidelines strictly. You can have a different design with different LCBs, test it and find that it is better. Am I clear? Okay. Now, you see this sectional area curve is so much related to how much area I give in the middle, is not it? Now, suppose I have got two sections, let us say midship section or midship section coefficient is the same thing. I have got one midship section which is like this is the center line, and I got another midship section which is like this. That is, this bilge radius is R1 and this bilge radius is R2. R2 is bigger than R1. Bilge radius. What does this indicate? R2 will have a lesser section than R1, is not it? Suppose this was made with R2, how will the curve look for R1? Or let's say this sectional area curve corresponds to R1, the lower sectional area, lower radius, therefore higher sectional area. Now, I think that no, if I have a larger bilge radius, flow around the bilge will be smoother. So, I give a larger bilge radius, my sectional area will drop, but I want the same volume. So, if I drop my sectional area to here, let us say, how will my curve change? My forward and aft will become fuller. I will have a large parallel middle body, but my forward and aft will become fuller. Do you understand that? It will become like this. This area that I lose will have to be made up here and here. Which is better? You see, now my parallel middle body has increased, good from production point of view. I have reduced, I have made the bilge radius large, thinking that the bilge flow will be smoother, but in the process I have made my shoulders very prominent. And if I have large shoulders, I know I will get into trouble. So, you see what I wrote in the first page. I talked about CB first. Now, you see how CP and CM are playing roles. CP, what is prismatic coefficient? Right. In these two cases, you can see that Cp for this case, the dotted line case, is higher because C midship is lower, right. So, this dotted line, that is lower Cm or C midship, lower midship area coefficient coming out of larger bilge radius will give me lower Cp, sorry, higher Cp, and this is having lower Cp. So, whatever may be the CB, for the same CB you will have a range of CP based on your Bill's radius, and you can see that lower CP is better than higher CP from shoulder point of view. Of course, you can then say that I will go to the extreme and make the C midship as 1, then my CP is same as CB. I got a, is that desirable? I cannot go lower than that. Is that desirable to have a CP like that? That is not desirable, because you are introducing large separated flow, because the bilge will be now totally discontinuous. You will introduce large separated flow. So, there is a compromise between the CP you can give and in the range of CP that you can give. You have to make a compromise in the range of CP that you will give. And normally for merchant ships, your bilge radius is limited to between about 1.5 to 3 meters. You do not go beyond that. Okay. Then next important item in this is the water plane area, water plane curve, load water plane, LWL curve. We have seen the sectional area curve. We have already discussed the role of half angle of entrance in the class when we discussed wave making resistance. Do you remember? Half angle of entrance we talked about, that determines how smoothly the hull is going into water and what will be the wave crest. So, LWL, if it is smooth at FP, if this angle is small, half angle of entrance is small, then it is always advantageous. And therefore, this follows for our curve 2. You see the curve 2 that we showed before, though it has a prominent shoulder, its section area curve here has narrowed, which leads to a finer angle of entrance. Okay.
So we can go that 19.28 which you told, you can go below that also.
Yeah, you can go. That 19.28 is for a pressure point. Okay. So, load water line curve is also an important parameter. Now, then next comes the fore body of the ship, fore body shape. We have 3 fore body shapes which are extreme, and we have to choose one of them or in between them. One is called typically a fore body section shape, which is like this. This is called V form, like a V. Normal ships that have a shape like this will have a section like this. The section comes down like this. The other one is what you call a U form section, more like a U. This case, because it will be difficult for one to close the sections, this will look more like this. The end profile view will look something like this. Sections are more U. And lastly, you will have the bulbous bow. Okay. And if you draw a section here at the FP itself, you will have this bulb. As we have discussed, in both these forms, as compared to V form, the volume comes down, right. If the volume comes down, imagine the sectional area curve. We are providing volume, but below the waterline. So, the waterline becomes smoother, unlike here in V form waterline is sharp, is more blunt, more angle of entrance, half angle of entrance higher in this case, lower here and lowest here. So, as far as the waterline is concerned, this comes much better with the bulbous bore, then U form, then V form. So, typically the wave making resistance for a well designed bulb, I mentioned that again, for a well designed bulb will be the lowest because of the bulb as well as because of the load waterline shape. A little worse than this will perhaps be U form, but this will definitely be better than this, because the waterline shape here is better than what we would get here. So, this is better than this from calm water resistance point of view. Then you may ask me, why is this used at all? Resistance is not the only characteristics for which ships are designed. You can imagine a vessel slamming, the forebody going up and down. The impact pressure will be much larger here, largest here and least here. So, there is a distinct structural advantage in a forebody like this with regard to structural design as well as structural safety. Okay. So, you have to look at the forebody shape and finally, the aft body shape, the type of stern you have. But aft body shape is not considered to have large impact on resistance alone. Why I say this is that if you design a reasonably good aft body as a conventional aft body, you will not have any penalty on resistance. If you do a bad aft body, of course, it will have penalty everywhere, but the aft body is primarily designed with flow considerations such that flow onto the propeller is good and it does not generate vibratory forces. That is how aft body is generated. Okay. So, these are some of the considerations we take while designing the hull form, so that we get favorable resistance, calm water resistance. Then after the hull form is designed, we go and do the model test. From model test we extrapolate for full scale, and then during trial condition you compare whether you have got good prediction or not. But this is not enough for us to draw up a hull form. So, what else do we have? How do you know the resistance at the very early stage, or for a ship for which resistance data is not available, tank test data is not available? What methodology do we follow to estimate the resistance if such data is not available, tank test data is not available? Over the years, over the last I would say nearly 70-80 years, a number of ships, series of ships have been designed and tested. So, one of the methods of estimating resistance is the so called series ship method. Let me explain what it is. Oh, if I have ships of the same family, that means I define a ship shape in a particular manner, like I can say my forebody will have V form, aft body will have a cruiser stern, etc. By some means I define a ship and try to generate more forms using that family, that ship as the basis. That means I can broaden the ship only, not increasing the length, use the scale and broaden the ship, or I increase the block by distributing the area equally over the entire length or in a particular manner over the entire length. So, sections get full. If I am making a higher CB ship, then section gets full in a gradual manner. Then I can call that ship to be of the same family as the original ship. That means I have a parent ship or a number of parent ships, and I generate from this parent ship more ships. Do you understand what I am saying? Can you understand? If I have certain ship parameters as constant, like 4 body shape, I decide I will have 16 forms with the same 4 body. I can say that of these 4 will be constant L by B ratio, but each set of 4 will vary in L by B ratio slightly. That is, first 4 let it be 7, second 4 will be 8, third 4 will be 9 and fourth will be 10, let us say. Similarly, I can say B by T ratio to vary slightly, but the form remains same. I will just geometrically change the shape. Similarly, I can say my LCB will be 1% aft or at midship or 1% forward. I do this by not changing the shape, but just by swinging the sectional area curve and putting the sections where the new sections should be there as to change the LCB position. Can I do that? It is possible to generate a large number of ships using the same form characteristics, but changing the main dimensions. Am I understood now?
Could it be described as Xerox copies of different sizes?
No, no. Let us say I just increase the breadth, then each section is pulled out. It is not a Xerox copy.
Xerox copy with different sizes. I change the size.
No, only one dimension I am changing. It is not scale. It is not scale change. It is just one dimension I am changing. I can change L by B, B by T, I can change block coefficient, I can change LCB. By changing, general nature of form remains same. Okay. This is called the series, developing a series of ships. So, if I generate a number of ships like this and test them in a tank, what I get is a matrix of ships for which all resistance data is available. And if I can present it properly, then for any intermediate dimension, I will be able to tell what will be the resistance. This was the thought way back in 1950s, 40s and 50s. So, we had a number of series starting with the Taylor series and later modified to what is called Taylor-Guttler series. These are basically V form ships for high speed operation, used mostly in naval vessels to date. Till now, the naval vessels are built very near the Taylor-Guttler series, where the speed requirement is high and you can get a really good prediction of resistance and also get a hull form. Okay. But this is not very useful for merchant ships for the reasons already we have discussed. Resistance is high. Naval vessels use it because they operate normally in 2 or 3 speed conditions, a sprint speed, then a normal this thing, but merchant ships do not work like that. So, these vessels are not good for merchant ships, and so in 1950s and 60s a series was generated in the David Taylor model basin of USA called series 60. A number of models were manufactured and tested, and we got huge amount of data on series 60, not only on resistance. These vessels have been tested for sea keeping, for resistance in waves and maneuvering. So, large tests have been conducted on series 60 vessels, and a storehouse of data is available in open literature. The resistance data was published by Todd in 1963 in SNAME. Now, series 60's basic feature is the forward sections are U-shaped sections. So, they have reasonably good resistance characteristics, and they are good to start a hull form for at the initial stages of designing a vessel. Then we have two more series I will just mention to you, BSRA series, which is BSRA standing for British Ship Research Association. This series was developed in the 60s and published by Lackenby in 1966 RINA, Royal Institute of Naval Aeronautics. This series has the typical nature of, again coming back to V-shaped sections. They are more V-shaped than series 60, and they have been designed over a wide range of block coefficients. You can get BSRA series forms up to up to 0.8, 0.82 block coefficient. Then we have another series called SSPA series developed by the Swedish tank, and there are other series, I will not mention them, but these are the four most important series ship data available in open literature. There are of course series data available for trawlers, smaller vessels, and also for other types of vessels such as planing craft, etc. If your design is more near a series ship, then you can use the corresponding series ship and estimate the resistance and from there powering. But many times you do not get a ship which is very near the series. Therefore, it is difficult to estimate resistance. So, the next method is statistical data. That is, if you got one thing you must have understood by now, that all these series that I have mentioned, they are all non-bulbous forms, and today we have ships with bulbous forms. Therefore, present day ships perhaps will be better than most of the series ships, and therefore, this data cannot be used with any reliability for modern ships. They tend to overestimate the resistance if you use it for a modern day ship. So, the best way to do is to find out what does statistics say. If you have got large number of ship data, then can we make a statistical analysis and say my ship, since large number of ships of all types fall in a particular pattern, the resistance falls in a particular pattern, maybe my ship will fall in that. So, I can estimate my ship resistance and say it will have plus minus 5% actual resistance. Now, this has been done rigorously by Holtrop, NSMB, Netherlands Ship Model Basin, Holtrop, and there is another chap called Mannen. They have published their statistical data analysis in the 1984, 82, 84 ISP, International Shipbuilding Progress. What they give you is they have analyzed slow form ships, fast form ships, bulbous bows, non-bulbous bows, cruiser sterns, transom stern, stern immersion, various draft conditions with appendages and without appendages. Large amount of data has been collected together and whole set of regression analysis has been done, and knowing your ship parameters of all these quantities, they give a method by which you can estimate the resistance. That is so far the most reliable method of estimating resistance for ships as of today. We do not have, I have mentioned this before, we do not have a fully theoretical method for predicting resistance as yet. So, statistical analysis is the best way to get the resistance of a ship if we do not have the tank test data. Okay. If there are no questions, then we will stop here. Thank you. আমি বন্ধ করে দিয়েছি।
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus. but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology, and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. That ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shaped their mind and body, a collage of events that was a synthesis of competition and cooperation, a collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting, and the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls, with their blocks and wings connected by charming catwalks, remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous, and holistically inspiring, where students, wherever they might be from, invariably come into their own, developing their individual talents, honing their skills to take on challenges with confidence, so they can move ahead in fulfilling their dreams. What makes IIT Kharagpur so unique is its environment. Undiluted by the diversions of metropolitan surroundings, the close-knit campus life enhances the entrepreneurial and innovative spirit of the achievers-to-be. In an environment that is so stimulating, it is only natural that down the years, IIT Kharagpur has consistently produced well-rounded individuals. Many of them are celebrities in their own right. Holistic grooming has had a lot to do with this. So, no matter which walk of life they choose, the IIT KGPite stands tall. And so does the institution that bred him, in majestic splendor. The alumni of this institute command global respect. Their distinguished presence at the helm of global giants is a matter of national pride. For the students of IIT Kharagpur, it is impossible to erase any scratch of memory about their alma mater. In fact, some come back to invest sentiment, pride, and money, to see the institute they call home rise to even greater heights, structurally, functionally, as well as holistically. Their singular aim is to make IIT Kharagpur an institute, whichever way you look at it, par excellence. A man's journey into quiet accomplishment and the Hall of Fame starts with the right step. And the training and placement cell of IIT has been the efficient facilitator in this regard for over 30,000 graduates. Having placed more than 95% of its students in a wide range of industries consistently for over 2 decades, it is no wonder that the institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire. Indeed, in this Golden Jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.